Hey, good morning. Okay, so we are going to look at one of these problems on problem 6.3 in the numerical methods book, and specifically, we're just going to kind of focus on the Newton-Raphson. So this is going to be an example of creating a Newton-Raphson function. So what we have is we have this function, and we're trying to find the highest real root. So let's just kind of start doing stuff. So right off the bat, I'm going to create a file called the Newton-Raphson. Let's open this up. Now, we're supposed to make a function of this. We're going to look at this part B right here where we're creating a function. But at first, let's just kind of start solving it. So part A is kind of something you have to do regardless. And so I'm going to say f is equal to x cubed minus 6 times x squared plus 11 times x minus 6.1. Now, I happen to know that it's going to squawk at me when I use fplot, so I'm going to go ahead and put the dot operators here so that it doesn't get upset with me, so it can do things in vector form. Fplot likes to be efficient, and it'll get mad at me there. So I'm going to do clear all, close all seals, and then clear the screen. I like to do this at the beginning of every problem just so I don't have anything kind of residual floating around. Okay, so let's plot this thing. Let's go fplot of f. So we'll just do the defaults. We'll run that and see what we get. And here we go. So I'm going to turn on grid on, zoom on. Okay, so when I run that, we're looking for the highest real root. So it looks like it crosses here, here, and here. Does it cross again later? I don't know off the top of my head. So let's go ahead and go from, say, 0 to 100. I don't know, I'm just making up a number. I think we can go through and figure this out, actually, that with this x cubed, it's going to, with that being a positive number, it's just going to increase. So that makes sense. So coming in here, we're still, okay. Yeah, so it looks like this is truly, so the answer is going to be right around, let's figure it out. The answer is going to be, what, 3.0, 3.047, 3.0468, something like that, right? So that's the answer. So here, actually, let's just write that down for giggles. Graphically, approximately 3.0468-ish. Okay, so now we kind of know roughly where we're talking. So I'm going to, again, go from here to, let's go to 0 to 5, just so that the plot's a little more reasonable. It's scaled a little more easy. And this is it. Okay, so let's look at the Newton-Raphson method. So the Newton-Raphson method, the basic idea of the Newton-Raphson method is to use a point. We're going to pick a point. Doesn't matter where. Well, that's a lie. It does matter where. But you can pick any arbitrary point, and then it'll use a point and that slope to project down to where it crosses 0. Then it's going to come up there and project down where it crosses 0, back and forth. So mathematically, it ends up being super easy, right? Basically, you're going to say for I is 1 to a whole bunch, right? Which is going to be way overkill, totally unnecessary, but just for giggles. And xr is going to be xr minus the function at xr divided by the slope at xr. And that is the Newton-Raphson method. That's the whole thing. So in order for this to make sense, we have to have an initial guess. So what would be a reasonable initial guess? So we can guess really, really close to the answer. One thing, the nature of this, if I guess over here, so again, remember, Newton-Raphson kind of finds the answer that it finds. We don't get to pick it. So if I guess of 0, it's going to use that to project to here, come down, and it'll probably find this solution over there. And we want to find the highest solution, so we have to pick something close to that. So let's pick, say, 3.5. 3.5. And we can play around with what other answers we get when we pick other things. Okay, so now we're almost good to go, right? We have an initial guess of 3.5, and we say the new guess is going to be the previous guess minus a function evaluated at 3.5. So you plug in 3.5 into here, calculate that function, and then divided by the slope. We do not have the slope, and this is the problem with Newton-Raphson. So we're going to have to calculate the slope. So we're going to have to create a function is at x. So this is the derivative of x. So this is going to be, what, 3 times x squared minus 12 times x plus 11. I think I did everything right there. 3x squared, take the 2 minus 12x, and then plus 11, and then this term goes away. Okay, so now this should work. Actually, let's go ahead and look at this. We're going to look at XR. We're going to do a format long G to make it nice and long, and we're going to look at it, and we get an answer of 3.0466, and we're 0468, 668. Yeah, I forgot the 6 in that. That's all it is. So, yay, it works. So that works, okay? So here's our problem. We have a couple problems. A, this is not a function, right? This is just the method. This is not actually a function, so we need to make this a function. And B, we did 10,000 iterations. Newton-Raphson is usually really good at converging quickly, so we need to figure out how to make that converge much more quickly. So how do we decide when it converges? Fundamentally, the way we decide it is converged is when from one iteration to the next, the answers are basically the same. So I'll show you an example of this. Let's go back this way after 10, and I'm going to turn this format, put this up here, okay, and I'm going to look at every output. So there we go, and let's look at what this looks like. So my first guess is 3.19, then 3.06. So you can see there's a pretty non-trivial change there. It's changing, but then all of a sudden, like from here to here, it takes way off into the 1, 2, 3, 4, 5, 6 decimal place before it even changes. And then here, it's, holy cow, it's good to like the 13th decimal place, right? And so on. So we can probably stop somewhere in this time frame here. Okay, so how do we decide how to stop? Well, first off, I can go back to having this be a whole bunch. And actually, no, I'm not going to do that. What we want to do is we want to set the ES and the EA. So what is ES? In this case, ES is equal to 0.5 times 10 to the power of minus, and then does it say how many sig figs we should have here? 3 significant figures. Okay, so we're going to go minus 3 for sig figs. We could actually put sig figs and then say sig fig is equal to 3. That's probably actually a good form right there to go ahead and do that. So now we have our ES, and so now the whole point is we're going to do this until our EA is smaller than ES. Well, we haven't calculated EA. So what is EA? So EA is just simply the difference between my current guess, so XR minus my old guess, I can call it XR old, divided by XR. So that is EA. There's a slight problem there, right? And that problem is that we don't have this yet. So the way I do this, I'm just going to say XR old is equal to XR. Okay, so let's walk through this logic and think of what this means. We're going to go through, and I have an initial guess for XR. And the first thing I'm going to do is I'm going to put that kind of away. I'm going to grab hold of it before I make any changes. So I have this XR old is equal to XR. And then I'm going to calculate a new XR based on the function and the slope and the actual value of XR. And then I'm going to say, okay, what was the difference between those two? So it's going to say XR old, and then it calculates the new XR, and then I'm going to look at the difference between those two. And then importantly, I'm going to divide by XR because, again, a difference of 0.01 is lovely if your answer is 10,000. It's pretty horrible if your answer is 0.001, right? And so there we go. We have the fractional or the relative change. And then the idea is that we're going to do something like if the absolute value of EA is less than ES, then break. And that should work. And just for giggles, let's come in here and let's look and see how many it did. So we're going to run that, boom, and it took 4 iterations to get to that point. So if I wanted, say, more sig figs, say I want like 8 sig figs, and it's going to take 6 iterations, so it takes a little bit more. Okay, so we'll go back to 3 sigs because that's what it was asked for. Okay, so this is lovely. It is okay. I don't like it. What we are doing is we're taking a for loop and making it look like a while loop. Well, if we want it to look like a while loop, let's just make a while loop. And so that's what I'm going to suggest. Let's go through here and just turn it into a while loop and see how it goes. So what's the basic idea there? Instead of this for, I'm going to say while. And what am I doing while? It's while my error is large, right? So while the absolute value of EA is bigger than ES, so as long as this EA is larger than this threshold, just keep going. Okay, so I'm going to get rid of all this. And there we go. So do I need to increase my I or N or anything like that? No, because I don't have a counter. I'm just continually making this better. Okay, so when I run this, I'm going to get an error. What is my error? It says, I don't even know what this EA is, but I calculate it right here. But again, think of the first pass through this loop. It's going to come in here to this loop, and it's going to say, while the absolute value of EA is greater than ES. Well, I don't even know what EA is. It doesn't calculate it till later. So let me move this down again. My way of dealing with this is I'm just going to make up a number. You could go through and be smart. Like if it's the first time, then do so and so. What I've picked up on doing is I said EA is equal to 999. And the reason I do that is if I look at it afterwards and I see this 999, that's a flag that something went wrong because this clearly should not be 999. But 999 is for sure going to be bigger than whatever I put here. So this should work. And boom. Oops. I'm displaying I and I'm not calculating I. So there we go. So there it is. It did this. I don't know how many times it took to take it because I got rid of that counter, but that's all right. Okay. So that's it. That is a pretty flushed out version of the Newton-Raphson method. But it is still, unfortunately, not a function. If I can highlight that. So how do we make this a function? And let's take a second to do that. So I did it this way on purpose, not on accident. When I'm making a function, the first thing I'm going to do is make it a script, flush it out, debug it, get it to work, and then convert it into a function. So I'm going to, right off the bat, I can bring a new script. I'm going to take, so basically what I'm dealing with is, I'm going to go up through here. I'm going to put all this over here, right? And the Newton-Raphson is now going to be a function output, or I'm going to call it XR, my root, my X root, is equal to Newton RHAPS1 of the function. Well, we're going to get into what goes into there in a minute. Okay. So eventually I need to call it. So I'm coming back here. This is what I have, right? So my function is that. I'm going to move this up here just for clarity's sake. Okay, the function and the slope. Okay, and I'm still going to plot this out here graphically, Newton-Raphson method. Okay, so the Newton-Raphson method is going to be a matter of calling XR is equal to Newton-Raphson of stuff. Okay, so what stuff do we need to pass it? So what stuff does it need? At some point in time, it needs obviously the function, it needs the slope, right? So put that up there. So these are going to be passed in. So we have the function, slope. Now with Newton-Raphson, the other thing you need to give it is a starting point. So I'm going to give it my XR as a starting point. And then lastly, and then lastly, we need to tell it how far to go. So there's basically two ways to do this. One option is to give it the sig figs, and then let it turn around and calculate this ES based on that. I'm actually kind of inclined just to go ahead and pass it ES. The thought process being is if I want to make it sig figs, I'm going to come in here. Let's go back in here. And I'm going to pass it the function, the slope, XR, and ES. The advantage of this versus sig fig is if I wanted, say I didn't want to do it on this, say I just wanted ES to be, 0.0001. And actually, now that I think, is that what the problem asks? No, again, it asks for 3 sig figs. So in this case, that does not make sense, but it gives you the option to do that. So I'm just going to do ES here. Okay, so let's come back into here. So I'm passing it this. I don't need that. I'm actually going to go ahead and get rid of that. I'm passing it all this stuff. I don't want to plot it inside there. I don't need that. Now, please get in the habit. This is actually what I do. The first thing I'll do is I'll copy this and I'll do that. I'll comment out that first line. So now if I type help, if I come into here and if I say help Newton-Raphson, it'll give me the name of that, right? And now ideally, and what I want you guys to really do, is turn around and say like where f is equal to a function solved as slope is derivative of function xr is initial guess and yes is the convergence threshold. And you can other amazing comments that make things clear. Okay. So now, XR, we are passing that, our initial guess, we don't need that. I definitely do not want to display anything from the function. Please get in the habit of not displaying things from the function. I'm going to go ahead and put an end to the function. It turns out when you have a standalone function, you don't need that. But it seems like it's becoming a good habit because when you do the function at the end of your script, it does need that. So this should be good. I think this is kind of the content of what it's looking for. It's going to return this XR when it's done. So we're going to save that because functions do need to be saved. And we're going to come over here, we're going to run it. And we're going to find out if it works. Boom, there we go. So the XR of that. So that works. We go through, we're creating this plot and doing all this stuff now outside the function. And it's just calling the function with information. So if we talked about what if we guess of 0? So if we guess of 0, I suspect it's going to give us this root right here. So like 1.1 and some change, right? So let's run that. And yep, 1.05. It gives us that. And what if I want to find this root right in here? So I just start at like 1.8. So if I start at 1.8, run that, and there we go. So approximately 1.9. So what your initial guess is makes a huge impact on where you find it. Basically, I mean, you can start to kind of practice a little bit. So I suspect anything past this threshold, this breakpoint right here, will give us this answer. Again, 3 should give us the answer just fine. There you go. That's all. And that is it. So again, the function, you want to have a standalone function because that's what's being asked for. Now you could have turned around and put this at the bottom of this script, and that's how we're going to turn in the homework most of the time, but eventually you want to have this function built up. So here we have this function. You have the comments that make it easier. Again, now that I've made those comments, if I say help XR, help Newton-Raphson, it's going to give me all the stuff that I put in there. So this is for you, right? This is your stuff that you're putting in there to remind you, to jog your memory of what you did. Again, XR and ES and XR, what order you put those inputs, you can do whatever the heck you want. And so having a little help there to remind you. I've made plenty of functions where it seems super obvious at the time, and then a year later when you go to use it, you're like, which order was it? And so if you just have a help function, it just helps you remind you real quick which it is. But that should be it. That is a Newton-Raphson function. That is part B on steroids. There you go.